All right, so yesterday, what we took a look at is we took a look at this expression. We said, hey, we now have a way, if somebody gives me the Ka, but maybe I need the Kb, I have a way to get to the Kb if I have the Ka, or vice versa in this case. And one of the things that's gonna happen, once again, is we're gonna have to really just pay attention to the equilibrium that is before us. If I see H3O plus as a product, I'm going with the Ka. If I see hydroxide, I'm in my head, I'm saying I need, in this case, the Kb in this case. So the sort of problem that we could have could be something that looks like this right here. I got, in this case, potassium fluoride. They're gonna place the potassium fluoride in water. And the solution is kind of here, so you don't have to look at the solution. I'm gonna just walk you through it and let you see kind of the logic of how we're gonna go about it and take this problem and make it a fairly easy problem. The first thing I'm gonna do is say, okay, well, you know what? I got a 0.2 molar solution of potassium fluoride. It's an ionic compound. I need to break this thing into pieces to kind of figure out, who's gonna go through and have that hydrolysis reaction. So I'm gonna start off by maybe looking at the potassium and say, okay, potassium, if I look at how you interact with H2O, liquid, and keep one thing in mind, it might make your life a little bit easier here. Go here. We're going to end up getting KOH aqueous plus H plus aqueous here as well. And the one thing I wanted to kind of point out that might make your life a little bit easier is sometimes I notice that students might have a hard time like, should this be hydroxide or should it be, in this case, the hydronium cation or the H plus? Easy. You're positive, it's going to kick out the positive thing of the water. In this case would be the H plus. We'll see with the anion, it's always gonna kick out the hydroxide. So just kind of look at the charges here. Now one of the things that I can see is I can see that, this is not gonna take place. There's no reaction. And we said it's no reaction because you happen to be a strong base. And therefore it will never kind of exist as this connected between or showing the potassium hydroxide kind of connected together. They'll be completely dissociated. And this thing says that they must be stuck together. So you're not taking place. But what I can see that is going to take place is if I go to the fluoride and I interact that with water, H2O liquid, going in equilibrium, we're going to produce HF, AQ. Hey, you're negative, so this has to be hydroxide down here as well. You're a weak base, so this is fine. From this point on, it's going to be pretty easy. Because all I'm going to do is I'm going to set up my ice expression. So here we go, our ice table. I can go in and say, okay, well, what's the initial concentration in this case of the fluoride? That's going to be 0.20 M here. I don't care about you because you're a liquid. You're going to be 0, you're going to be 0. You're going to be minus X, you're going to be plus X, you're going to be plus X. You're going to be 0.20 M minus X, you're going to be plus X, and you're going to be plus X right here. Which means that one of the things I'm going to do here is I'm going to come down here and I'm going to do the following. I'm going to write my equilibrium expression here, because once again, AP is going to give me 1 point for write it down. So I'm going to say K is equal to products of reactants. Everybody raise their coefficients. No solids, no liquids. So I got HF, OH minus, divided by, in this case, the F minus concentration. What does this need to be? It needs to be Kb. Because we clearly see that, once again, it's hydroxides here, so I gotta make sure that I work with Kb here. But if you look at the actual problem, and in this one, I made it too easy for you. I provided you the Kb. Now I could have made this tricky and gave you a Ka right here. Just use the equations. Swap it over and make it a Kb in this case. So now I'm home free, because all I do is really substitute in, and then eventually solve this problem. So I'm gonna go in here and say, hey, you're 7.2 times 10 to the negative 4 is equal to, well, what do we got right here? We got X times X divided by 0.20 M minus X, and get rid of the M here since I'm trying to solve this thing. And then once again, I'm going to go in and see if I can get rid of the minus X, and I'm going to multiply this by 2, or by 100, which is going to give me 7.2 times 10 to the negative second. Yes, it passes the test. because this is still, when I multiply this by 100, this is still going to be a larger value. So that means I can get rid of that minus x here. So I can kind of remove this. And therefore it prevents me from having to go through the quadratic. And we can all be in agreement that from this point forward, I don't need to go through. Now, you're going to see the answers in the notes, but can't we all agree that we can also now figure out x? We can take the negative log in this case and get what the OH concentration, the POH is. So try 14, I got the pH. So the only thing I'm showing you here is nothing's really changing. Only thing I got to do is kind of figure out, which one's going through the hydrolysis, and just make sure I'm careful with the actual equilibrium constant I'm choosing here. So on the notes, you'll see right here the exact same thing kind of playing out. Here goes my ice table that we just created right there. And then you'll now start to kind of see the solution working itself out. So the x was 0.012. Once again, proving the fact that if I take the k times 100, it passes the test of still being, in this case, the initial concentration is still larger than those two, so get rid of the x. That minus x sitting right there, solve for the x. And once again, I've got my hydroxide concentration. I can use this way of doing it, or I can take the negative log. Once again, multiple ways to get there. But also we're going to find that the pH is going to end up being 12.08. Simple enough. Let's look at the next problem. And then after looking at that problem, we'll probably kind of just go to our homework and see if we can knock out as much of our homework as possible to minimize how much we will have of the weekend. Hopefully we won't have much. All right, let's look at this one here. So once again, without using what we have in our notes, we're just going to see once again, can we solve this problem? And for this particular problem, if we look at it, what do we got? We've got ammonium chloride. So that's a ionic compound. That's my cation, that's my anion. I need to figure out in this case what's going on. And for some of you, you're going to be able to go in here and say, you know what, I know that the chloride in this case is going to have absolutely no interaction with the water. And the reason why I know that is I know the H is going to stick to this thing, which means I'm going to have HCl over here. And as soon as I kind of recognize that in my head that that's going to be HCl over there, then I don't really care about the rest of this problem. I can go in here and say, you know what, this is absolutely no reaction. So that's not going to lead to anything. It's really going to be, in this case, the ammonium cation. And it's interacting with H2O. And once again, one of the things that I told you is that I already know what has to sit on that side over there. If you're plus, you got to be the hydronium cation. So I already know that that's going to be H3O plus that's sitting over here. And of course, if I remove one hydrogen going from here and deposit it onto the water, that means that, hey, you're just going to be in H3 in this case. Home free. I'm ready to jump right into my ice table, ICE. In this case, I got 0.10 M. I got 0, 0. I got minus X, plus X, plus X. I got 0.10 M minus X. I got plus X. I got plus X. And let's see what we got going on here. Equilibrium expression, products over reactants. Everybody raise their coefficients. No solids, no liquids. So I'm going to go here and say, you know what? K is equal to NH3 times the H3O plus, all divided by, in this case, NH4 plus. And then I'm going to look up here and I'm going to say, look at that. Got my KB here. So I'm going to go ahead and put KB there. And then we just solve it. I just take the value in this case, and it gave me the KB, 1.8 times 10 to the, what is that? Negative third. 1.8 times 10 to the negative third is equal to N, well, let me substitute in. X times X divided by 0.10 minus X. And then, well, great, we can just solve in this case for X. Can we be done? What?
We need the K.
Thank you. That is H3O plus. I can't use KB. KB is going to cause me to lose my points in this case. I got to recognize that once again, you are a acid here. I need, in this case, the Ka to sit here. That is not my Ka. But once again, I do easily have a way to go from my KB to the Ka. Ka times KB equals KW. So I'm just going to go and get the right K that I need in this case. So for this one, let's say Ka is equal to KW divided by KB. KW I know is 1 times 10 to the negative 14th. The KB in this case happens to be, what do you say, 1.8 times 10 to the negative, we said it was 3, yes. And now we're going to have what we need in order to solve this problem. Let's see. I'm not working with that thing. I need my TI calculator. My TI is all the way in the back of the class. I'm telling you, I know exactly what you young ladies are going through. To walk back here and all the steps that it took me to get back here and how you gotta like take the steps to go down the hill to Founders. Walking back here kind of like really makes me feel like I'm a part of the journey that you have to take from class to class. So just want you to understand that. In solidarity with you, I kind of get a sense of what you go through. All right, here we go. Let's see what we got. I got 1 second E now. This is beautiful negative 14 divided by 1.8. Oh, come back to me. There you go. Over there, second E to the negative 3rd. So now what I get is I get something like this here, 5.5, and how many sig figs? Looks like 2 sig figs, so that's 5.6 times 10 to the negative 12. And to tell you the truth, I like this better. The reason why I like this one better, because I know for a fact that if I multiply E by 100, am I getting anywhere close to that initial concentration? No, that's a great thing, because it means that I get to drop that X in this case from the actual expression, because I know that ultimately we're going to have here is we're going to have kind of like X times X divided by 0.10 minus X, which is now equal to the 5.6 times 10 to the negative 12. But I get to easily, because if I multiply that by 100, it's not getting anywhere close to that value. I get to get rid of that X, and now I can just solve this. And once again, we are home free. Is everybody okay here? Because this is what we're about to jump into. We're about to jump into our actual homework and do some problems. And as you're going through the problems, you are going to solve the problem, and then after solving the problem, you're going to come and see me. And you're going to say, hey, Mr. Olson, this is what I got for my pH. And then I'm going to take a look at it and let's say either this, or I'm going to do what? I don't know. I don't like that. It's got to be something more gentle. What's more gentle than that? We'll just say like, maybe, how about that? Kind of leaning towards the wrong side in this case. And you'll go back and we'll try to see if we can correct it. So let me explain.